All right, good morning, everybody. So before we get started on the group work today, we need to finish up what we didn't get to last time. So we started talking about things that affect acidity, and I said that there were four factors. What were those four factors? One's on the board. Right. The element effect. What else? Resonance effect. What else? That has to do with the element. Hybridization and inductive. That's right. And inductive comes into electronegativity a little bit. Now, one of the things that you all will confuse, because everybody does every year, is the element effect and the inductive effect. Okay? And so we're going to try to distinguish the two. The element effect is the effect that we see when that element bears the negative charge. Okay? That's important. The inductive effect has other elements in it, but those elements don't bear the formal negative charge, and so that's why we distinguish the two. Okay? So the element effect is really what you learned in general chemistry as the trends in the periodic table. We know that as we go in a period from left to right, the acidity increases. Right? We know that methane is less acidic than ammonia, which is less acidic than water, which is less acidic than HF. We know that. And we know that at this point simply because that's what you were taught in gen chem or high school chemistry, right? We know that periodic trend. We also know the periodic trend within a family that as we go down the family, the acidity increases. We know that HF is actually a weak acid. HCl is a strong acid, HBr is a stronger acid, and HI is the strongest acid in that family. Okay? And so the reason that we see these element effects, or these periodic trends, is because of the element effect. Okay? So last time we talked about when we're going to compare acids, right? Let's say we're looking at HF versus H2O. How do we compare those in terms of acids? We look at the conjugate bases, right? And so we know that the conjugate base of HF is F minus, and we know that the conjugate base of H2O is OH minus. Now, based on that, which one of those conjugate bases is the most stable? F minus or OH minus? F minus. Why is F minus the most stable? It's the most electronegative, okay? And so we know that F minus is able to accept that negative charge better than oxygen. Now, oxygen's pretty electronegative, but it's not the same, right? And so we know that the most stable conjugate base belongs to the strongest acid when we're doing these comparisons, okay? Notice in both cases, the element that bears the negative charge is different, oxygen versus fluorine. Okay? Now this is going in a period. What about if we're going in a family? When I'm looking at F minus versus Cl minus. So let's say we want to compare HF versus HCl. So I've drawn the two conjugate bases. Which one of those is the most stable anion? It is not F minus. It is Cl minus. Why is Cl minus more stable than F minus? I thought we just established that F was the most electronegative element. That's a true statement. It's larger. That's exactly right. When we are in a period, the atom size changes just a little bit because we're dealing with the same valence shell. I mean, yes, fluorine gets a little smaller, but not huge. But what happens as we go down a family? The valence shell is changing, and so what's happening to the size of it's growing larger, right? So bromine, well, they did bromine, I'm sorry, but chlorine would also be this, right? So the atom below fluorine, which would be chlorine, right, is bigger than fluoride. Why does that matter? Why does size matter here? Okay, that's right. So if we take that negative charge and spread it out over a larger volume, that is a more stabilizing effect. it also has to do with solvation. Bigger atoms are easier to solvate than small atoms. Okay, and so you have that stability in aqueous solution anyway. Okay, and so we're dealing with all these in solution. Okay, so the element effect, put it in language for me. What do you think, Amber? The element effect. How would you describe it to your neighbor? Conjugate bases. Uh-huh. Okay. So we are going to look at both electronegativity and size, depending on whether we're comparing acids in a, what's horizontal? Period or family? A period, and then we're going to be looking at size when we look at a family, right? Okay. So we know that HF is a stronger acid than water, but HF is a weaker acid than HCl. We know that. Do you need to know the exact pKa values to do that kind of analysis? Absolutely not. Okay? So we've got the element effect. And we can see those pKa values here in this slide. HF has a pKa of 3.2. That's just slightly more acidic than some acetic acid derivatives. So it's slightly more acidic than vinegar. HCl is strong, HBr is strong, HI is strong because they're all negative, right? But they're not all identical. HI is the strongest acid in the family there. Okay. There are also inductive effects. An inductive effect is a stabilizing effect due to electronegative atoms that are bound through sigma bonds, and they do not bear the formal negative charge. So for example, if we are looking at ethanol versus 2,2,2-trifluoroethanol, there's the structures. Look at those pKa differences. Rough math, what is it? About 3.5. Is that large or small? Pardon? Yeah, the difference. Is that a huge effect or a small effect? What does P mean? It means to take the log, right? So it's 3.5 orders of magnitude difference. That's big. If somebody came to me and said, I'm going to give you 3.5 orders magnitude in your pay, oh, man. Thank you, right? So, yeah, this is a huge effect, but it is not the element effect. And how do I know it can't be the element effect? What do I do? What's the first thing that I'm going to do? I'm going to draw the conjugate bases, right? In both cases, the negative charge is on the same element, O minus. I can't make a distinction here, right? So the difference has to be the inductive effect. Those fluorines are doing something to stabilize this that these three hydrogens can't do. What might that thing be? How? Absolutely. We know that fluorine has an electronegativity of 4. Hydrogen has an electronegativity very similar to carbon. So trifluoroethanol is going to be more polar in that regard, right? It makes the whole molecule more acidic in this particular case. Okay? And so if we draw it out, what we notice is that the bonds between the carbon and the fluorines are very polar, right? And that puts a partial negative charge on each one of these fluorines. So what does that do to the carbon? It puts a partial positive charge on it, which does what? It pulls electrons from its neighboring carbon, which puts a slight positive charge on that, which is right next to a negative charge. If I take a negative charge and I put a positive charge next to it, is that a stabilizing or a destabilizing effect? It's stabilizing. Basic physics from high school told us that opposite charges attract. And things only attract if they're stable, right, and low energy. Doesn't work the other way. So that's why this works. One of the things that you need to know, the further you get away from the actual negative charge in the conjugate base, the less the inductive effect is. The inductive effect falls off rapidly with distance. The closer these fluorines are to that oxygen, the better. So in fact, actually, if I had difluoroethanol where the fluorines were on this carbon instead of this carbon, we would actually have even more stability, and it would be more strongly acidic. So distance matters. What about if we had chlorines on there versus fluorines? Would it be more acidic than ethanol or less acidic? It'd be more acidic, but would it be more acidic than trifluoroethanol or less acidic? Less, and why? Exactly, right? So those things come into play with the inductive effect. I don't know how else to say it, and every year I say it, and people still get it wrong. So don't be the first year, please, okay? This is not the element effect. Yes, there are elemental differences between these two, but these elements don't bear the formal negative charge, okay? That's the important thing. Does that make sense to everybody? Okay. The next factor is the resonance effect. So if I look at ethanol, ethanol has a pK of 16, pretty close to water. Acetic acid, however, has a pK of about 4.8, 4.75, depending on which text you get it from, right? Where do we get acetic acid in our daily lives? Vinegar, right? And we know it's acidic. We use it in our cooking to acidify foods, right? So we know that it is, we know by definition it's the stronger acid just from our experience. But notice the difference. Let's just round that up to 5. How many orders of magnitude is that difference? Yeah, that's a big, big difference, right? Now, if we look at ethanol, we look at the conjugate base, that negative charge is located on one oxygen atom and one oxygen atom only. Is that true for acetic acid? No, it is not. And in fact, our ability to draw a single resonance structure makes all the difference in the world. So if we look at acetic acid and we draw the conjugate base, we know that we can push these electrons to draw this other equivalent resonance structure. And simply being able to draw that one additional resonance structure stabilizes that anion so much that we get 11 orders of magnitude stronger acidity. That's pretty cool. Just one resonance structure. Okay? So this effect is actually quite prominent, even though we're listing it at number 3. It seems to have had the largest effect of acidity, right? Of all the things that we've compared. Right? So resonance effect. So we've talked about the element effect, we've talked about the inductive effect, we've talked about the resonance effect, and what remains? Hybridization, right? And so we're going to be talking about the different types of hybrid carbons. So let's look at some of these. We've got ethane. What's its hybridization? Everything's sp3 hybridized, right? How about ethylene? sp2, and acetylene, sp. Notice what happens to the pKa's. Gets more acidic as we go from left to right. So sp3 hybridized hydrocarbons are going to be very, very weak acids. sp hybridized hydrocarbons are going to be stronger acids, right? By a little bit or a lot? By a lot. I mean, if I'm looking at this, right, that's 20, I like this math, that's real easy, right? 25 orders of magnitude. It's 10 to the 25th. That's a lot of cash, right? Remember, a billion's 10 to the 9th. This is great. So what's changing? What is changing as we move from left to right is the percent S character of that hybrid orbital. sp3 really means 1 part S, 3 parts P. So what's the percent S character? 1/4, right, or 25%. sp2, it's what? 1/3. And sp, it's a half or 50%, right? What's the difference between an s orbital and a p orbital that's doing all this? What's the shape of an s orbital? Spherical, right? And what's the shape of a p orbital? Kind of like a peanut. Yeah, it's kind of like a dumbbell, as I like to think of it, right? Kind of like a stretched out 8. Yeah. And what's in the middle? The dots? Right? So we got an s orbital, right? And we got a p orbital. What's here? A node. And that's where the nucleus sits. What does that tell us? That tells us that electrons in the p orbital can never get really close to the nucleus. Does that exist there? No. So if I take that as my nucleus, the electrons can get closer to the nucleus in a p orbital than they can, or excuse me, in an s orbital. Make sure I got that right. The electrons can get closer to the nucleus in an s orbital than they can a p orbital. Okay? It does. And why? You do know why. What is in the nucleus of an atom? Protons, which have what charge? And electrons would be like to be near positive charges or away from positive charges? Near. So if I'm an anion and my electrons are in something that has a lot more S character, my electrons are going to be closer or further away from the nucleus? Closer, which is a stabilizing effect. If my electrons are in an orbital that has more P character, my electrons are going to be closer or further away from the nucleus? Further away, which is a destabilizing effect. Okay? Now we can visualize that using that fancy piece of software that I got, that I showed you all the IR spectra. Well, it can also calculate a whole host of other things. And one of the things that it calculates for me are electron density maps. That's what these are. And your book actually uses these as well. And it turns out that if you think about it, if I have a negative charge and I put it closer to a positive charge, am I going to see more negative, or is it going to kind of cancel out? It's going to kind of cancel out, right? And so it turns out that negative charges in these calculations turn out to be kind of this red color. What happens with this red color as we move from left to right? It gets fainter, meaning that the negative charge is actually closer to the nucleus. So you can see this quite clearly in these pictures, that this is very red, this is, you know, kind of in between, and this is, it's almost hard to see any red. It's kind of yellow, right? That color map, if you will, tells me that those electrons in the acetylide anion are closer to the nucleus. Okay, and so they're more stable. So, which one of those anions would be the strongest base? Yep, this one over here, the one with the pK of 50, right? Very good. So, let's repeat. The element effect is what? Okay, if and only if they bear the negative charge, right? The inductive effect still deals with electronegativity, right? Okay. But what? Okay, so it will never bear the formal negative charge, right? And also, the element effect has to do with size when we're talking about family, right?
So does that mean that, like, in this row, that, like, I would be
In this family? Mm-hmm. Yes. The acidity, as we go down a family, increases. And across. Yeah.
Where's the line going, like, compared to, like, sulfur? You know, because, you know, it's further, it's bigger, but it's not as electrolyte. Where does that line kind of get drawn as far as which one's stronger?
Well, sulfur will definitely be more, or like H2S is definitely more acidic than water. So
comparing that to, like, HF?
It's weaker.
Weaker, okay.
Mm-hmm. Remember, the trend is this way and down, so it kind of goes, and it's a fuzzy line, right? And that's okay. You don't need a hard line to figure this out, right? So real quick, I want you to explain the pKa differences of those molecules with the indicated hydrogen. The indicated hydrogen is the one that you're going to remove to draw the conjugate base? So the first thing you got to do is draw the conjugate bases for each of those molecules. And I want you to explain the differences in the pKa. Who are we missing today? No, nobody. Okay, I miscounted. So what's the first step in all of these? What do? We draw the conjugate bases. So the first one, we're going to remove that indicated hydrogen, and we're going to have that. That's going to be the conjugate base, that lone pair on that carbon, right? And we know that that has a pK of 50. What am I going to do for the second one? Same thing. I'm going to remove that hydrogen. And what am I going to do for the third one? Remove the hydrogen. Right? Does that in and of itself explain the pKa differences? No. Do I have any element effects that I can see here? Not yet anyway, right? Okay. Can I draw a resonance structure for this? No resonance. Is there any inductive effects? No. It's all carbons and hydrogens, right? What can I do here? I can draw a resonance structure, and how would I do that? Okay. And that makes a pretty good difference, right? That's the resonance effect. So I've got resonance. Can I draw resonance structures here? You bet I can. I can draw that. So can I draw any other resonance structures? No. So I have the same number of resonance structures here. Why do I see the huge difference in pKa? Which is what effect? That's right. Notice we can have multiple effects. This has both resonance and element. This only really has resonance. Now this is element because the negative charge is formally born on oxygen, right? In both cases here, it's on carbon. That's right.
For the first resonance structure, like, I'm confused on how we made it do that. Like, maybe I just, like, the negative that came over to the...
Because I can take this negative charge and I can form a pi bond between these two carbons by breaking that pi bond.
Oh, okay.
So I have a double bond, single bond, lone pair motif. Yeah. Okay. So we've got an exam next Wednesday, right? These types of comparisons will be on that exam. How do you identify the stronger acid? How do you put the acids in increasing order or decreasing order? Make sure you read the question. Okay? I could ask it like, which of the following is the strongest? Which of the following is the weakest? Put them in order, rank order from least acidic to most acidic or most acidic to least acidic. Okay? All of those are fair game. The example tests in Blackboard are exactly how I ask questions. but those are retired exams, and you will not see those questions again. But it gives you an idea of how an exam will look. All right. Let's go ahead and start working on this. Why don't you two pair up? Here it's an element effect and a resonance effect.
So just on this one.
Yeah, this one it's not an element effect because in both cases the negative charge is on carbon.
Right.
But here I have the negative charge on carbon, and here I have the negative charge on carbon, and here I have the negative charge on oxygen.
Okay.
So it's both resonance
And
and element. Yep.
I don't understand.
Yeah, so we removed the hydrogens, right? And drew the conjugate. Where did you draw the conjugate? Oh, okay, I see how you got it. Okay, so we drew the conjugate bases, right? And then we asked ourselves, what can we do to stabilize that conjugate base? Here, I can't draw resonance structures. I don't have the inductive effect. I don't have the element effect, right? Because all of them are carbon.
Okay.
So
So
that explains why that has the highest pKa. But here, I can draw a resonance structure for it. But in both cases, those resonance structures have the negative charge on carbon. Here, I can draw an equivalent number of resonance structures, right, 2, just like for here. But in this case, I have one structure that puts the negative charge on carbon and one structure that puts the negative charge on oxygen. So this, even though it has resonance, it also has the element effect.
So the element effect is like changing the formal charge
Mhm.
for the resonance?
The element effect is when we have the negative charge on an element,
Okay.
right? Here it's on carbon, here it's on oxygen.
Okay. So that makes this one stronger or weaker than this one?
That makes this, well, it's got a pK of 19.2, right?
Okay.
This has a pK of 43. This is a stronger acid.
This is strongest of all.
Because the conjugate base is more stable here than this conjugate base.
And why is it more stable?
Well, if I have a negative charge, right, would I rather be on oxygen or carbon? Right, because of electronegativity, right? So that's why. That make sense? Perfect.